our focus question today. Our focus question says, how do kinematic quantities change as a pendulum oscillates? Now, you've just seen it. You've just looked at it working back and forth, haven't you? At time t equals 0. What's going on here? At time t equals 0, we've pulled it back and this is where it's sitting. We are going to let it go, right? Which way is it going to be? Moving. So let's talk about this. What is a pendulum? A mass attached to a massless string that swings about a vertical equilibrium position. Pendulums approximate simple harmonic motion. Simple harmonic motion is the name of the game for this chapter. Restoring force on a pendulum is the component of the weight tangent to the arc of the object's motion. So what does it mean? It means if I pull it back this way, if I pull this guy back this way and let it go, which direction does it want to go? The opposite way. That is the restoring force. The restoring force would be the other way. Tangent to the arc, so notice that I had it going perpendicular to the string, don't I? It's always going to be tangent to the arc, proportional to the displacement. In other words, the further I pull it back, the more it's going to want to go back into its original equilibrium position. Does everybody understand the equilibrium position for a pendulum is at the bottom? This is my equilibrium position. It wants to go back eventually to being straight down, doesn't it? And resting. Okay, so what does it say? It's not true simple harmonic motion except for small amplitudes. They say less than 20 degrees or so. Usually what physics says, most physics books say is about 30 degrees or less, okay? But it's not true simple harmonic motion unless it's a very small angle. That's the biggie, small angle. All right, so the first thing we look at is, what is the maximum value? What is its displacement? This is its displacement. This is its velocity, right? This is its acceleration, kinetic energy and potential energy. So where is it displaced to? In this guy, we've pulled it all the way back to the right, haven't we? So it is at its max displacement to the right. Does everybody understand that? It is maximum to the right. If I were to take this guy and pull it back, this pendulum, this is what I've done. Right here, it is at its maximum displacement to the right, isn't it? Is it moving? At this moment in time, what's its velocity? 0. Why is it at 0? It's fixing to do what? What's the green arrow about to do? Switch directions, yes. Okay, so the velocity is at 0, and we know the velocity is at 0 because it is about to switch directions, isn't it? What about its acceleration? So let's look at its acceleration now. Let's go slow. Look, that arrow is at its longest or its shortest right here. It's at its longest. So we know the acceleration is at its max. And which direction is the acceleration pointing now? To the left. It is max and to the left. Now, let's put the energy graph up. What do we notice about the kinetic energy here? It's at 0 because it's not moving, isn't it? It's at 0. What do we notice about the potential energy? It's at its max. Okay, so now I'm going to let this run until we get to the bottom. Oops, not quite far enough. going on. Well, I didn't quite get it there. Here, fine. There we go. All right, so let's look at this. This is at time 2. Time 1 is 0. Time 2 is t, which is the period, over 4. Big T is period, okay? It's 1/4 of its period, isn't it? Why do I say it's 1/4 of its period? What did we say a period was? From the center to here, back to the center to here, and back again, right? So how many sections is that? 1, 2, 3, 4, right? So do you see why I say it's 1/4 of the period? When it goes from here to here, it's 1/4, isn't it? Okay, so it's 1/4 of the period. Now, what about its velocity? We don't have that. What direction is the velocity pointing? Okay, it's to the left. So this is at equilibrium. The displacement, it's now at equilibrium. The velocity is to the left. Where's it going its fastest? Where did we say it was going its fastest? Look at the kinetic energy. Kinetic energy is maxed, isn't it? If the kinetic energy is maxed, what does that tell you about the velocity? Also at a max, isn't it? So it is maximum velocity to the left. Kinetic energy is at its max. What about the potential energy? Look at the graph. What do we notice about the potential energy? 0. If the potential energy is at 0, then what does that tell you about the acceleration? It's at 0. Why is it at 0? Because what's happening to that yellow vector? It's straight up, and then as we start going again, what automatically happens to it? Now it's going to the right, it goes back straight up, and then it goes to the left. So what's happening to the acceleration vector at that exact moment? It's changing from one direction to the other, isn't it? So anytime something is at 0, typically it means that it is switching directions. Does that make sense? Can you see it? All right, so this is T sub 3. How far into the period are we now? We've gone here to here, back to here again. There's 4 sections. 1, 2, 3, 4. So we've done 1, a quarter. Now we've done another quarter. So how far into the period have we gotten? Halfway. So this is big T over 2. Now, displacement. It is going to be maxed all the way to the what? It started maxed to the right, so now it's all the way to the other side, so it's maxed to the left. Yes. So it's maxed to the left. Okay. Now, what is the velocity at exactly that point? When it gets to its highest, to the left, what's happening? Okay, it's switching direction, so what is the velocity going to be then? 0. Okay? What is its acceleration going to be? All the way to the left, what is that? What do you see about that yellow arrow? Anytime we get to the top ends, what do we know about the acceleration? It's maxed. Yes. But which direction is it maxed this time? Yep. Max to the right. Okay. What do we know about the kinetic energy? If it's all the way up to the left, what do we know about the kinetic energy now? 0. And what do we know about the potential energy? It's maxed. You getting the idea there's a pattern here? Are you noticing? All right, now it's back at the bottom again. So if it's back at the bottom again, time 4, how far through the period are we now? A quarter, a half, now we're where? 3/4 of the way through. All right. What position is it in now? Look at the little picture. What position is it in here? Equilibrium. What's its velocity at equilibrium? It's maxed. Now, is it maxed to the left this time? It's maxed to which direction? Yep, maxed to the right. Good. We can see that. If the velocity is at a max, what's happening to the acceleration vector at the bottom there? It's switching directions, isn't it? If it's switching directions, then what's the acceleration at that point? 0. Okay? At the very bottom, at equilibrium, what do you notice about the kinetic energy at the equilibrium point? It's at a max because it's going fastest there. What about the potential energy at the bottom? 0. Yep. All right, so we're on phase 4, right? We started here, we came to here, we went back up, we're back down again, and then we're going to finish up by going all the way up. So, position T sub 5, and we've gone all the way through one what? One cycle, what do we call that? One period. So this is just now T. Where is it at? Back where it what? Back where it started. Yep, so it is, the position is max to the right. You ought to be able to fill this in. Isn't everything here going to be exactly the same as that, what? First row? Max to the right, the velocity is 0 because it is switching directions, right? Acceleration is going to be at a max to the left because it wants to now move to the left. It's stopped at the top, so the kinetic energy is 0, and thus the potential energy must be maxed. Do we understand how this works? Good. Period of a pendulum. We talked a lot about the period of a pendulum, big T. What did we say the things were that affected the pendulum? Period. How long the string was, right? What else affected it? We checked 3 things. We checked mass. Did mass affect the period? Nope. Did the length of the string affect the period? Did gravity affect the period? Yeah. So length of the string and gravity affected the period, didn't it? The bigger the gravity was, it changed it. When gravity went up, the period went down, didn't it? In other words, it did this instead of doing this, didn't it? However, when the length of the string got longer, as the longer the string got, the longer the pendulum got, right? So what we know is as L goes up, the period goes up. But as gravity goes up, the period went what? Down. So this is a direct relationship and this is an inverse relationship, isn't it? And you'll see that. 2 pi times the square root of L over G. That is the period of a pendulum here. Okay? So as we go, as the length of the string goes down, the period goes down, doesn't it? Here we go. Shorter period, longer period. However, gravity does the opposite. As gravity gets bigger, period gets shorter. As gravity gets lower, period gets longer. So we've got that inverse relationship for gravity and the direct relationship for the length of the string. It totally makes sense if you think about it. The stronger gravity is, the faster it's going to make it stop, right? And then swing it back around. However, the longer the string is, the longer it takes to get back, doesn't it? All right. So, questions so far? Any questions? Yeah.
Where's the 544 for pre-cap? Because I never received it. And it's due tonight.
You got them all the same day that you got 5-3. I gave you 5-3, 5-4, and 5-5 all that same day. Remember, we did 3 sets of notes that day.
Yeah, but I found
You should have gotten, it was all,
oh, so good.
it 5-4, 5-5 homework was stapled to your notes packet.
Oh, it's stapled to
Yeah.
the okay.
Okay, it took me a sec, but that's what happened. You good?
Yeah.
Okay. All right, so let's look. And guys, you need to understand this chart right here. You need to be able to think about what this chart is. You need to know the places. I know you are not on your phone. The places in this, yeah, the places on this chart where kinetic energy is 0, where gravitational energy is 0, where the velocity is 0, where the acceleration is 0. You need to know all of those things, right? So this chart is kind of important to know, because next time we're going to be talking about springs, and we're going to have this exact same chart, except we're going to have it for springs next time. Okay? This is a very, very short unit. Now, here's my next question for you. We've got about 7 or 8 minutes left. You have a test next time on momentum and energy, don't you?
Wait, both together?
I'm going to put it together because we don't have time to do 2 separate tests. It's going to be a little of both, so that should help you with the energy part and momentum if you know it. You had a review to do. That was what you were supposed to have done and worked on over the weekend, right? Your momentum review. I need to know if you have any questions on any of that. Yeah, y'all had this. I promise you did.
Can I see?
Yeah, you had it.
I don't know.
The key is on Canvas for you.
Are you on?
I gave you the key for on Canvas. You need to make sure you understand all the questions and that you understand how to do momentum-free responses, okay? How to do a momentum-free response. Make sure you understand. Highlights for momentum, remember that impulse is F delta T, right? Area under the force graph curve, change in momentum, impulse.
Right, delta.
Delta is just a triangle.
Okay.
Just a triangle. Technically speaking, delta, if you look at the Greek letter,
I just can't.
it's this and it's got a little extra over here.
Yeah, I just can't remember the symbols.
Yeah. Delta, that little triangle means change.
I still don't know what it means. I think.
What, epsilon? This?
Yeah, but also.
Oh no, sum of. This means sum.
Yeah, that one's.
That is a
sum.
summation symbol.
That other one is what? The one that looks like a backwards 3.
That's just energy.
Okay.
In physics too, it's entropy. This just means sum of, to add up.
Okay.
Capital letter epsilon.
Yeah, you just kept putting that in your letters. I'm like, what?
Oh yeah, you should ask.
They're always, so the answers to the questions are always accurate. They're
Acceleration due to gravity on the moon is 1/6 that of the Earth. Period of a pendulum of the moon is measured to be 7.6 seconds. Find the period of the pendulum on Earth. Can we do that? How do we find period? This, by the way, is on your formula sheet. Look at your formula sheet. Do you know where the period is for formula is on your formula sheet? Pendulum stuff, guys? Pendulum stuff is over here in this small little chunk. If you'll notice, see the period formula? Period is 2 pi over omega, okay, which we'll get to eventually. 2 pi, for a spring, it's m over k, but for a pendulum, T sub p, it's that fourth formula down, T sub p is 2 pi L over G. Everybody good with that? That's the one formula you need for pendulums right there. Fourth down, T sub p. We'll use the other one next time, T sub s. So, we know we're going to be looking at this. 2 pi times the square root of L over G. Does it bug anybody that I'm using capital L here and not little l? Like on the formula sheet? You know L is length, right? Okay, so let's plug this stuff in for the moon. I want to plug stuff in for the moon. I know that this is what? 7.6. This is 2 pi. And we don't know L, do we? Do we know G? We know it's 1/6 of G on Earth, don't we? So this would be G over 6. Do you agree? G over 6? So how do I solve for L? Do we know what G is on Earth? 10, right? Okay. So maybe we should put 10 in here. The thing we don't know is L, do we? So this is 10 divided by 6. Okay, so now can we solve for, so this is the moon. How do I solve for L? Okay, so I'm going to divide by 2 pi. And divide by 2 pi. Now what? Square. So that goes away, and I'll square this. Multiply by 10 over 6. Okay, so that's the last thing I need to do is multiply by 10 over 6. Multiply by 10 over 6, so that goes away. All right, so I'm left with L equaling whatever that mess is, right? So let's figure out what that is. So we have what? 7.6 divided by 2 pi. Going to square that. Multiply it by 10, divide by 6. I get a length of 2.44 meters. Now, will that help me find the period of the pendulum on Earth? Yeah. So T on Earth, so here's Earth. We're going to use the same formula all over again, aren't we? 2 pi, only this time we know what the length is. Is the length of the pendulum going to change between the moon and Earth? No. The only thing that really changes is gravity, right? So predict for me. We said gravity had an inverse relationship, didn't it? So is the gravity on Earth bigger or less than the gravity on the moon? Bigger. So if the gravity is bigger on Earth than on the moon, do we expect the period to go up or down? Down. It's an inverse relationship, isn't it? So if the gravity on Earth is higher than the moon, then the period ought to be shorter. So if you get something that's not shorter, you did something wrong, didn't you? So the length is 2.44. We took that from here, and we're going to feed it in over here, and we're going to divide by gravity, which is 10. So what do we find is the period on Earth? And period should be in seconds. Somebody calculate that for me. Okay, so 3.10 seconds, right? Period's going to be in seconds. So the period on Earth, T sub E versus T sub M, right, is 3.1 seconds. Okay, so let's look at another example. We have a 0.5 kilogram mass suspended from a 40 centimeter string, creating a simple pendulum. The mass is displaced at an angle of 15 degrees from the vertical equilibrium position. Yes. Yeah. Calculate the frequency of the pendulum. So the first thing we need to know is frequency. Frequency, if you look on your formula sheet, look at the second in the second column. Look at the second formula in the second column. It says frequency is equal to what? Or period is equal to 1 over frequency, isn't it? So frequency is equal to 1 over the period. So if we can find the period, so this is an important formula to know, isn't it? It's just the inverse of the period. All right, so we need to find the period. Period of a pendulum is 2 pi square root of L over G, isn't it? Does the mass even matter? Nope, they've given me information I don't need. I don't need that, but I do need the string. 40 centimeters is how long? Guys, this is all in meters, so 40 centimeters is how many meters? .4 divided by gravity, which is what on Earth? Because we're on Earth, aren't we? 10. So what do we get for the period? You get about 1.3? 1.25, okay. So this is 1.25 seconds. But I don't want the period, I want the frequency. So the frequency is then going to be 1 over 1.25, which is what? Yep, 0.8, and that is per second, isn't it? So seconds to the -1. Do you know what seconds to the -1 is? What do we usually measure frequency in? Does anybody know? Hertz. Frequency is hertz, okay? If you're in band, you do music, frequencies in hertz. So second to the -1 is the same as saying 0.8 hertz, Hz. Okay, so this is the same as this.
Do the answers always make sense on like physics questions that they give you?
Do the what?
Do the answers always make sense? You know what I mean?
Yeah.
Like, will you ever get like if you told me to find the height of a ladder, right? And I got a negative number, that wouldn't.
Yeah, that would not make sense. They would have to make sense, yes. In that regard, it would have to make sense. Calculate the height of the pendulum above the equilibrium position. Okay, when it reaches its max displacement. Guys, to do this, we need to know what's going on. At its max displacement, we're going to do this through energy, okay? It says draw a free body diagram of the mass at this position. So let's start with free body diagram. Normally it would be straight down, wouldn't it? That's equilibrium position, isn't it? Now it says, what happens when it reaches its max displacement? Max displacement is going to be somewhere over here, isn't it? Do you agree? Max displacement is going to be at some angle theta. Now, it wants the height between here and here. In other words, this is the height above. This is h. You need to look at this from an energy standpoint. At its max displacement, what is its velocity? At its max displacement, what's its velocity? 0. It's stopped there, isn't it? It's at 0. So if we look at it from an energy standpoint, what is its velocity at the bottom? At the bottom, at equilibrium position, it's going its fastest, isn't it? Everybody focus. At its equilibrium position, at the very bottom of its swing, watch it. Max kinetic energy, max potential. Max kinetic, max potential. Max kinetic, max potential. So at the bottom, it has all of its kinetic energy. At the top, it's all been converted to what? Potential. So we can do this as an energy problem. Does that make sense? So we know that 1/2 mv squared is equal to mgh, right? And the m goes away. We don't care about the mass. So what we want to find is h, don't we? Now, do we know its max velocity? No, we don't know its max velocity, do we? So we're kind of in trouble here because we don't know h either. We got to know one or the other. So let's go back to the free body diagram and then we'll go back to this picture. It said draw the free body diagram. So what forces are going on at its max displacement? What forces do I have in a pendulum? Force of gravity, so I have mg going downward. What else do I have? Tension, but is the tension going straight up at this position? Which way is the tension going? It's going along the string, isn't it? So the tension is going along the string this way. Do you agree? Okay. Now, what are the things we do know here? They gave us the mass. Great. We didn't even need that. We don't know the velocity. The only thing we know is the angle it's displaced at and the length of the string, right? Okay. So we've done this before. You just don't remember it. The length of the string right here is L, isn't it? Guys, the length of the string is also L right here. What we're looking for is H, which is this chunk of it here. Is that not correct? We're looking at H from here to here. So here's my question for you. What is this length here? If I knew that length, couldn't I find the other chunk? Yes, I could. So we know this right here is theta, don't we? That's my theta. So this length right here would be L cosine theta, would it not? Isn't that how we normally find it? L cosine theta is this chunk here. So now how do I find H if I know that? What is the entire length of this thing? From here to here, what's the entire length? L, right? And if I take away the chunk here, and what is that length? Guys, we used trig to find that length. We just said that length was what? L cosine theta. Can't we find the height? Yes, we can. So let's plug in what we know. What is the length of the string? 0.4 minus 0.4 times the cosine of the angle at its max displacement. What was the angle at its max displacement in the problem?
Teacher, service interruption. At this time, all students going to the UNA field trip with Ms. Myatt's class, please report to the cafeteria. Thank you.
So it's 0.4 minus 0.4 cosine 15 degrees, okay? I'm recording this, I'll put the rest of it, there's only 2 more examples. Well, really the rest of this example, and then we'll be done, okay? All right, you should get what? Point 0.014 is what I get, meters, okay? Now, draw a free body diagram of the mass at its equilibrium position. So what would the free body diagram look like at the equilibrium position? Equilibrium position is at the very bottom, isn't it? That's our pendulum. So what is my free body diagram going to look like there? What forces are acting on it? And force of gravity is down, isn't it? So it's easy to find the tension on the string right there, isn't it? Okay. So we just say the tension is equal to the force of gravity, right? Is that it? No. You cannot do that. That's what a lot of kids do. You cannot do that. Why not? What shape is this flowing in? A circle, isn't it? So the sum of the forces here is not 0 because it's moving. It's just asking what's the tension at the bottom part. This is MA sub C, isn't it? That's equal to the tension minus mg, is it not? Well, MA sub C is the same as M what? Over R. But in this case, what is R? Length of the pendulum, isn't it? So instead of R, we could put L, couldn't we? Plus, so that's equal to the tension minus mg. So the tension ends up being mv squared over L plus mg. Guys, the tension is at its greatest at the very bottom of the arc, isn't it? Think about it. As it goes up, doesn't it don't you kind of feel lighter at the top of the swing? That's because there's not as much tension. And then as you hit the bottom, you feel the heaviest, don't you? That's because that's where the most tension is on the swing. You're pushed down the hardest there, aren't you? So the tension is the most at the bottom. So now what do we have to figure out? Do we know V? We're at that problem where we don't know V again. But guess what? We can find V here, can't we? So let's go ahead and find V. We knew that 1/2 mv squared is equal to mgh, don't we? M goes away. So V squared is 2gh. Take the square root. So the velocity is what? Square root of 2gh? Would you agree? So to find the velocity, we've got the square root of 2 times 10 times the height, which is the length of the string, which we said was 0.4. So what is the velocity? Yep, about 2.83, right? They're really not that worried about sig figs with at all with physics. It's just if I'm gonna, here's how I do it usually. If I'm gonna round it to 2 decimal places, then everything I'm plugging in, since I'm plugging this into another formula, I leave to 1 extra decimal place. That way I'm not rounding and rounding and rounding and rounding, because the more times you round, the more off your answer gets. So if I leave this to 2.83, when I plug it into the answer to this guy, because I'm going to take this velocity here and I'm going to plug it in right there, aren't I? I'll leave it to 2 decimal places, so now I can round this answer to 1 decimal place, and I know it's accurate. Okay, does that make sense? Okay, so the mass was 0.5. We know this is 2.83 squared. The length was 0.4. 0.5 times 10. So, let's multiply all that together. I get about 15. Yeah, I get about 15. So like 15.0 newtons. Is that what everybody else got? Yeah? No? Yeah. Okay. So let's look at the last question. Describe one modification to double the period of the oscillation. So if I want the period to go up and become twice the period, what are the things that I can do to make it twice as big? What is the formula for the period? You get this question, these types of questions a lot on the AP test in the multiple choice section. Of L over G. Can I change gravity on Earth? Not effectively. What's the only, 2 pi is a constant. What's the only thing I can change? Length. So what do I need to change L to for it to come out as twice as big? In other words, this is how you have to think about it. What number, because there's a square root over the L, isn't there? What number do I have to take the square root of to get to? 4, right? So I need to make this 4L become 2T. Does that make sense? Because if I want 2T here, I need it to be twice 2 pi square root of L over G, don't I? Well, for that to happen, if I take 2 pi 4L over G, that's exactly what happens, isn't it? The square root of 4 comes out. And this becomes that, doesn't it? So I need the length. I need to make the length how much longer? Guys, what does it mean to change L to 4L in terms of the actual pendulum? What does L represent? The length of what? The string. So I need to make the length of the string 4 times longer. Now, if you were not confined to Earth, we could change the gravity, couldn't we? What would I have to do to gravity to make this thing? Would I have to increase gravity or decrease gravity? I'd have to decrease gravity, wouldn't I? By 4 times, wouldn't I? I'd have to make it 1/4 the gravity, or 4 times the length of the string, right? So one of those two things, either the L in the top has to get bigger or the G in the bottom has to get the same amount smaller. Okay? So 4 times the length of the string or 1/4 the same gravity. Anybody have any questions about pendulums? Okay, so the big things you need to know is you need to know that relationship. This question right here is important. You see this a lot. Okay? You need to know how this guy, just to be super important, you need to know that that little chunk between here and here, that this little chunk right here is L minus, or is L cosine theta, and to find the height difference where the pendulum bob is above the bottom, that height difference is L minus L cosine theta. Okay? So you need to know that this chunk right here is this right here. That's important to be able to find. I've seen that a lot. You have to be able to find that, okay? Yep. Other important things, you need to know that this is a string and string moving, so it's centripetal force, right? So the sum of the forces is mv squared over r. Okay, got to remember that. You need to know frequency, although that's on your formula sheet. Know where to find it on your formula sheet. And you need to know this right here also, which is on your formula sheet, okay? So every formula we've used today so far has been on that formula sheet with the exception of the L one. The L minus L cosine theta to find the height above the swing, the bottom point, okay? So you have 2 problems to work in your homework, 11 and 12 on the 8.1. Speaking of, let me get rid of this. Oops, hang on. Notice that your homework is 8.1 exercises 11 and 12, and then you have workbook 6G and 6J. That's not a ton, is it? If you have not turned in your lab, if I do not get your lab by the end of the day tomorrow, I'm going to give you a 0. And I will not change it. I've got to get caught up on grading. We're getting close to the end of the 9 weeks. Did you realize that? This week and next week. We are in week 8. Next week will be week 9, and then week 10 is it. We actually have 10 weeks in this 9 weeks.
I did my lab, but my data, it's like, on the questions, my data is like, what's momentum, kinetic energy, etc., but it wasn't.
Was it close?
No.
Well, kinetic energy should have, the only place kinetic energy is conserved is in the elastic.
Yeah.
So it should have been fairly close. If it's not, then you just need to talk about why you think it wasn't.
Okay.
I mean, I'm not going to ding you for not having, data's data. That's what happens. But the fact that you need to talk about the fact that I know it should have been conserved or fairly close to being conserved, and it wasn't, and this is why I think maybe what happened.
I
Okay?
just wrote that it wasn't. I'll check it.
Okay.